Good morning, Anadol. Today we are going to discuss pumping lemma for regular cells. Pumping lemma for regular cells. Here, pumping lemma, the definition of pumping lemma is like this. Let L be a regular set. Then there exists a constant n such that if Z is in any word in N and modulus of Z greater than N, we may write Z is equal to UVW in such a way that modulus of UV less than or equal to N, for modulus of V greater than 1, and for every I greater than or equal to 0, U V raised to I W is in L. Furthermore, N is no greater than the number of states of the smallest DFSA accepting L. Here, if L is a regular set, if L is regular, there exists a deterministic finite state automata accepting L. Okay, that means if a language is regular, then there exists a deterministic finite automaton that accepts that language. That means that deterministic finite state automaton has finite number of states. Suppose that the number of states of that DFSA or deterministic finite automaton, the number of states is n. Suppose that the number of states of that finite automata, suppose that the number of states of deterministic finite automaton is equal to n. That means you have Q0 is the start state, Q1, Q2, etc. up to Qn are the number of states. And now, suppose that you have Z is equal to A1, A2, A3, etc. up to An. That means this is a string according to the language L. That is, the Z is a string and that string is having the literals or the components or the alphabet of these are A1, A2, A3, etc. up to N. A1, A2, A3, etc. up to N. And now, suppose that you are starting with state Q0. This is the start state Q0 and this is the start state. And initially you are in state Q0. Q0 on accepting A1, that is, you have a finite control and that finite control is initially in state Q0, and Q0 on accepting A1, it is moving to another state Q1. Okay, now the finite control is in state Q1 and after accepting Q2, it is moving to Q2, etc. That means on accepting Q2, it is moving on to state number Q2, and on accepting A3, it switches to another state Q3, etc. After accepting AN, it is moving to Qn. That means now you have Q0, Q1, Q2, Q3, etc. up to Qn. Okay, that is Q0 after accepting some, here you are having state say Qi. That means here Q0 after accepting A1, it is moving on to Q1. After accepting A2, it is moving to Q2, and after accepting, that is, here you have A1, A2, etc. up to AJ. not aj, this is ai. After accepting I number of I symbols of the string, that means after accepting each symbol, that means after accepting a1 it is moving to q1, after accepting a2 it is moving on to q2, and etc. After accepting ai it is moving to qi. And now here you have, say, after accepting ai it is moving on to qi, and now again it is accepting ai plus 1, ai plus 2, etc. up to, what is this, up to an. The string is a1, a2, a3, etc. up to an. That means here we have modulus of z. That means modulus of z means number of elements in that string. Number of elements in that string, that is equal to n. That is, here after accepting, initially it is in state q0. q0, after accepting a1 it is moving on to q1. After accepting a2 it is moving to q2. After accepting a3 it is moving to q3, etc. After accepting an it is moving to qn. That means now you have reached the final state. Suppose that qn is the final state. qn is the final state. qn is the final state. And this is the final state. Okay. Now the string is a1, a2, etc. up to ai. ai plus 1. Say, we can rewrite this as aj. aj, a, k, etc. up to an. Okay. To a. That means you have, say, in this string you have only n elements. You have only n elements in the string, and the number of states is also n. We are limiting the number of states to n. But here, say, q0 after accepting a1 it is moving on to q1, and q1 after accepting a2 it is moving to q2. Now here we have n plus 1 different states. See, here you have n plus 1 different states, but as per our assumption, the number of states of the finite state automata is n. But as we are tracing from q0 to qn, here we have q0 to qn, how many states are there? N different states are there. That means some state is repeating. That means, see here, you can write it as ai plus 1, ai plus 2 up to aj. It is repeating. That means some state qi is equal to qj. And after that, aj plus 1, aj plus 2, etc. up to an. That means here, see, once again you have to be very careful about this. The theorem is like this. That means if a language is regular, if you have a language which is a regular language, then definitely there is a deterministic finite state automaton which is accepting L. Okay. Now suppose that the number of states of the DF, say, or deterministic finite automaton, we are limiting that to n states. N. Suppose that you have n states, 1, 2, 3, etc. up to n, and the start state is q0, and you have taken a valid string z that can be accepted by the deterministic finite state automaton. Z is equal to a1, a2, a3, etc. up to an, and this is a deterministic finite state automaton which is accepting the language or accepting the string A1, A2, A3, etc. up to n. That means in your string, you have the length of the string is n. That is, Z is equal to A1, A2, A3, etc. up to n means you have Z is equal to modulus of Z is equal to n. That means the length of the string is n. Initially, this is in state Q0 or the finite control or the finite automaton is in state Q0 and Q0 on accepting A1, first symbol. After accepting that symbol, it is moving to state Q1. Now, after accepting A2, it is moving to Q2. After accepting A3, it is moving to Q3, etc. After accepting AN, it is moving to the state Qn. Now, as per our assumption, we have only how many states? N number of states. But here you have Q0, Q1, Q2, Q3, etc. up to Qn. Now we have how many states? If it has to accept a string of length which is greater than n, some states have to be repeated again and again. That's the point. That means if you have a finite automaton which is having n number of states, and if you are having a string which is having a length which is greater than n or greater than or equal to n, then you have to repeat. There should be some repetition of states. That means you have to repeat that states. That means at some point Qi and Qj will be the same. Okay, that means at some point it has to repeat. For example, I'll show you an example. Suppose that you are having, say, 0, 1, star 0. That means here 1 star 0 means here this one is repeating. That means here this is Q0 and Q0 on accepting 0 it is moving to another state, and on accepting 1 it is moving to repeating in the same state, and on accepting the next 0 it reaches the final state. That means if you are accepting 0 0, this is as per, this is Q2, as per this deterministic finite automaton, it will accept 0. Next is 0 1 0. Next is 0 1 1 0. 0 1 1 1 0. That means at this point, this is the pumping location. That means that can be pumped any number of times, any number of times, or can, that means this is the pumping site or this is the pumping location. At this point you can pump as you wish. That means this is, we are treating this as Q and this as V, not V. This is V and this is W. And say we are coming back to our theory. That is, our assumption is Z is equal to A1, A2, A3, etc. up to An. That means the input string is having length of n and the string is A1, A2, A3, etc. up to An. And our assumption is the number of states of the deterministic finite state automaton is n. And now you have n states, and Q0 after accepting A1 it is moving to Q1, and Q1 after accepting Q2 it is moving to Q2, and Q2 on accepting A3 it is moving to Q3, and likewise after accepting AN it is moving to Qn. Say Q0, Q1, Q2, Q3, etc. up to Qn, how many states are there? N plus 1 states are there. But as per our assumption, we have only n states. So as per pigeon hole principle, some pigeon has to occupy or some hole has to occupy 2 or more pigeons. That is pigeon hole principle. That means if you have n pigeon holes and n plus 1 pigeons, what will happen? What will happen? Some hole has to occupy more than one pinion. And that principle here we are going to apply. That means all these Q0, Q1, Q2, Q3 are not distinct. That means there is some point or there is some Qi where Qi is equal to Qj. There is some Qi and Qj are same. Both are same. That means, see, you have to be very careful about this. That means if L is a regular set, there is a deterministic finite order accepting the language. Okay. Now, as per our assumption that deterministic finite order is having n number of states. N number of states. Number of states is n. Say, suppose that n is equal to 10. 10 states are there. N is equal to 10. 10 states are there. Now, you have chosen, you have carefully chosen or Z is equal to A1, A2, A3, A3 etc. up to AN. That means this string, you have chosen a string which is having length n or length equal to 10. Initially, the start state is Q0 and Q0 on accepting A1 it is moving to Q1 and Q1 on accepting A2 it is moving to state Q2. Q2 on accepting A3 it is moving to Q3 and like that. Likewise, after accepting n it reaches the state Qn. Okay, Q0, Q1, Q2 etc. up to Qn. You have, and after this, you are counting the number of states through which you have your finite control has passed. Now, how many different states it has occupied when after traversing from Q0 to Qn or after reading each and every input, it passed through this much different states to different states. That means it has passed through these states. Now the different states are Q0, Q1, Q2, Q3 etc. up to Qn. How many states are there? N plus through n plus 1 states it passed through or it went through this much number of states and n plus 1 states, but we have only n states. And it was passed through n plus 1 states. And our assumption, as per our assumption, we have only n distinct or different states. But it has passed through n plus 1 state. That means you have only n states. But we have passed through n plus 1 states. Okay. At this point, we conclude that at some point it has repeated some state. Or that means after passing through one state, it has repeated or it came back to the same. That means there is some point where there is a loop. That means at this point, that means after accepting, initially this will be in state Q0. Q0 after accepting A1, A2, A3 etc. to A, it reaches Qi. And after accepting A plus 1, A plus 2 etc. to Aj, again it has returned to the same point Qj, and after that accepting Aj plus 1, Aj plus 2 etc. to An, it reaches Qn. That means here we are going to treat this as U and this as V and this is W. U, V, W. That means you have chosen Z is equal to N, modulus of Z is equal to N, and now you have split your input into Z is equal to U, V, W, and here you have V. This can be pumped any number of times. That means that can be pumped. That means just like that means if you can split this Z into U, V and W, then this point, this is the pumping location, then U, V raised to I, W is in L. That means this I can be 0, 1, 2, 3, etc. up to infinity. Okay, that means there is some point and that is called V that can be found. Okay, now come back to our pumping lemma for regular sets. Let L be a regular set. You have a regular set. That means a language is said to be a regular if it is accepted by some finite automaton, deterministic finite automaton. Okay. Then there exists a constant n such that if z is any word in L, z is any word in L, z is equal to UVW. Z is any word in L. As per that language, you have to choose a word which is in L. As per our language, you have to generate a word in L. And the condition is modulus of Z should be greater than N. That means you have how many states? N number of states and modulus of Z. That means the length of this string should be greater than N. We may write, you can split this Z or split this string into, you can split it into U, V and W in such a way that modulus of UV less than or equal to N. Here this is very important. Modulus of UV less than or equal to N and modulus of V. That means this V should not be null. This V should not be null. That means that the length of that V should be greater than 1. Furthermore, and for every I greater than or equal to 0, U V raised to I W is in L. Furthermore, N is no greater than the number of states of the smallest DFSA accepting L. Okay. And this is pumping lemma for regular sets, and the application of pumping lemma is to prove certain languages not regular. Not regular means there are certain languages which are not regular. If you want to prove that certain languages are not regular, first of all, it is a proof by contradiction. Contradiction means we assume that the language is in L, and from that we are starting, and if a language is in L, that means if a language is regular set, then you can easily choose a string. You can choose a string, and using that string is Z, and that is Z. That means you know how many states are there for the DFSA or deterministic finite automaton, that is N, and you have to choose a string which is having length greater than N, greater than the number of states, and after that you can split that Z into U, V and W, and in such a way that modulus of UV is less than or equal to N and modulus of V greater than 1, and for every I greater than or equal to 0, U V raised to I is in L. And we are, if you want to prove certain languages regular, first of all we have to choose a valid string from that set, and now after that we will prove that it is not accepting, or we are not able to write that in this form, U V raised to V UVW, Z is equal to UVW, you can't write. And from that assumption we will prove that it is not regular. That means first of all we are assuming that it is regular, and after that we try to write that in this form, Z is equal to UVW, and if you are not able to write it like that, then we conclude that it is not regular. Okay. Now, initially, I am going to prove that L is equal to the set 0 raised to n, 1 raised to n, where n greater than or equal to 1 is not regular. I am going to prove that 0 raised to n, 1 raised to n, where n greater than or equal to 1 is not regular. 0 raised to n, the language is when this language can in another way recognized when n is equal to 1, what will happen? The language is 0, 1. If n is equal to 2, 0, 0, 1, 1. When n is equal to 3, 0, 0, 0, 1, 1, 1. And when n is equal to 4, 0, 0, 0, 0, 1, 1, 1, 1, etc. This is the language. To prove that certain languages are not regular, see, here the proof is like this. Proof is like this. First of all, we assume that 0 raised to n, 1 raised to n is regular. Then I have chosen 0 raised to m, 1 raised to m. 0 raised to m, 1 raised to m. This is a valid string. If 0 raised to n, 1 raised to n is valid, 0 raised to m, 1 raised to n also is valid. Now, suppose that the number of states of the deterministic finite domain is n. I have chosen 0 raised to m, 1 raised to m as this is a valid string. If this is regular, it should accept 0 raised to m, 1 raised to m also, where m greater than n. M is greater than the number of states. M is greater than the number of states. And suppose that I am going to write here 0, 0, 0, then 0 raised to m, 1 raised to m, 0, 0, 0, followed by 0 and 1, 1, 1, etc. 1. Here m ones are there, here m zeros are here. Okay. Now see, listen here. Here one thing you should remember, that means here 0 raised to m, 1 raised to m, and I have carefully chosen this 0 raised to m, 1 raised to m, 1 raised to m, where m greater than n. M is greater than n. Okay, m is greater than n. So, as per our assumption, modulus of uv less than or equal to n. Here our assumption is modulus of uv less than or equal to n and modulus of v greater than or equal to 1. These are two assumptions. That means here we know that this is a valid string. We know that it is a valid string. 0 raised to m, 1 raised to n. 0 raised to m, 1 raised to n means 0 m number of zeros followed by m number of ones. 0 raised to 0 power m, 1 power m means m number of zeros followed by m number of ones. Okay. Now here you have initially m zeros followed by m number of ones. But as per our assumption, modulus of uv or modulus of uv is less than or equal to n. That means as m is greater than n, this much number of zeros are there, or m number of zeros are there, m is greater than n. So if you have to write this as z is equal to uvw, this uv portion, okay, uv portion is in this position. That means suppose that this is u and this is v. It cannot go after this. Why? Because modulus of uv, you are clubbing this u and v, and that together it should not be greater than n. It should not be greater than n. But m is greater than n. That means this w portion is also, this is w. Here, see, you should be very careful about this. That means you have to initially, we suppose that 0 raised to n, 1 raised to n is regular. And if it is regular, we should be able to write that in z is equal to uvw form. The condition is modulus of uv less than or equal to n and modulus of v greater than 1. Okay. Now, when we are splitting, now you have carefully chosen a valid string according to our language, that is 0 raised to m, 1 raised to m, where m greater than n, greater than n. That means m number of zeros followed by m number of ones. M number of zeros followed by m number of ones. Now, as per this, modulus of uv together should be less than or equal to n. That means here m is greater than n. M is greater than n. So n is coming up to this position, and this uv is coming at this point, and w is this point. Now this v is having only zeros. This v is having only zeros. Only zeros v is having. So if you take u v raised to I w, what will happen? This pumping location is only in this portion. That means only in the zeros, only in this position or at this point. That means you cannot pump 1. You are not able to pump 1. But 0 raised to m, 1 raised to n has to be accepted. There should be 2 pumping locations. That means 0 has to be pumped at the same time, 1 also has to be pumped. But at this point, you have, as per our assumption, u v raised to iw is not regular, not our grammar, because u v raised, this v is having only zeros. We came to that conclusion from where we have carefully chosen this 0 raised to m, 1 raised to m, where n greater than n. M greater than n. Now, you have split this into 0, 0, 0, 0, 1, 1, 1, 1, and now, as per our assumption, this modulus of uv should be less than or equal to n. Modulus of uv less than or equal to n. But m is greater than n. So, modulus of uv is coming up to this point. Up to this point, or it cannot reach that. From this point onwards, it is not able to reach. That uv is in this portion only. This uv. So, whatever be u and v here, if you are pumping that v again and again, zeros only can be pumped. There is no pumping of ones. So at this point, we can by contradiction, our assumption is not true. Our assumption is L is regular. So what is the contradiction? Proof by contradiction. What is the proof by contradiction? That is, this is not regular. This is not regular. Okay. Now, one more example. One more example is there. Prove that. One more example. Prove that 0 raised to n square. 0 raised to n, 0 power n square. What is the meaning of this? When n is equal to 1, L is equal to, when n is equal to 1, this is 0. When n is equal to 2, 0 raised to 2 square, that is 0 raised to 4. 0 power 4 means 4 number of zeros, then 9 number of zeros. 4, 5, 6, 7, 8, 9. and 16 number of zeros and like that. That is the language. That is the language. So how you prove that? How you prove that? 0 raised to n square. See, our proof is like this. Suppose that z is equal to some 0 raised to say 0 raised to n square. 0 raised to n square means n square number of zeros. Now suppose that you have 0, 0, 0, 0, etc. 0, 0, 0, etc. to 0. Suppose that this is that, this is z. We are splitting this into, say, this is up to this point, it is uv, and after that, suppose that this is w. This is uv and this is w. Okay, this is uv and this is w. Now 0 raised to n square means modulus of uv plus modulus of w is equal to what? N square. Modulus of uv plus modulus of w is equal to n square. That means 0 raised to n square means n square number of zeros. So I have divided this into two portions. That means here we have n square number of zeros. I have divided this into two, uv portion and w portion, and this uv portion is having, this is the length of uv and this is w, that is having length w. Okay, now suppose that this u is having, say, p number of zeros, v is having, say, q number of zeros, and suppose that w is having say there is a finite deterministic finite state automaton which is accepting this language, and the number of n is the number of states. Number of states of n is the number of states. Okay, now n is the number of states means now u is p number of zeros, v is q number of zeros, and w is, say, r number of zeros. Okay. See, if z is equal to uvw, when this is having length, say, n square, this is having, say, length n square, and suppose that we are pumping at this point uv, that means this uv is having length 0 raised to p 0, that means p plus q is the length of uv, and r is having length, this is having length r, and when you are pumping at this point, after the first pumping, suppose that this is 0 raised to n square, this is accepting 0 raised to n square, 0 power n square, next string it has to accept is 0 raised to n plus 1 square. Okay, now it is accepting, now this is accepting a string of length n square, or n square number of zeros it is accepting. Now the length of the string that has to be accepted is n plus 1 square. Suppose that the pumping location is this v. Now this v is having what? This v is having length n square. Now next string, that means this is u v raised to 1 w. Next string it should accept is Next is after this u v square w. That means suppose that this is the pumping location. It should accept a string or it should accept u v square w. That means that portion has to be repeated, has to repeat. And the length of this u v square w is length of u v w plus length of v. Okay. What is length of u v w? What is length of u v w? Length of u v w is what? N square. As per our assumption, n number of zeros plus what is the length of v? What is the length of v? As per our assumption, modulus of uv less than or equal to 1, and suppose the length of uv is equal to 0. Length of, even if the maximum length of that v is n. Maximum length of that is n. That means this is n square. That means length of uv square w is n square plus n. N square plus n. But the next symbol or next string it has to be accepted. It has to accept should be if 0 raised to n square is accepted, then after that it will accept 0 raised to n plus 1 square. What is n plus 1 square? N square plus 2n plus 1. That means if n square number of zeros is accepted, then the next string it has to accept is n square having n square plus 2n plus 1 number of zeros. But this value lies in between what and what? Length of u v square w is lying in between n square and n plus 1 square. This is a value which is lying in between n square and n plus 1 square. That means this is not a valid input. u v square w is not a valid input. So what is our conclusion? Our assumption was wrong. That means by contradiction we have proved that L is not regular. L is not regular. So till now we have been discussing pumping lemma and pumping lemma for regular sets. The pumping lemma is like this: let L be a regular set, then there exists a constant n such that if Z is any word in L and modulus of Z greater than n, we may write Z is equal to UVW in such a way that modulus of UV less than or equal to n, modulus of V greater than 1, and for every I greater than or equal to 0, UV raised to I W is in L. Furthermore, n is no greater than the number of states of the smallest DFSI accepting L. So this is the pumping lemma. This is the definition or this is the statement of the pumping lemma. And pumping lemma, I have proved pumping lemma, and after that, two examples I have shown you. With this, I am concluding this session and hope you enjoyed this session. And next I will come up with a new topic. Thank you.